Start. All right. So welcome back. I'll just welcome back to this video. So in the last video, we have looked at evaluation of like we have looked at two topics. So we have learned about two important topics in the field of object detection, right? So as you have, I'm just going to remind you that we are currently learning object detection. I'm currently teaching you object detection, the ability of computers to locate different objects in an image intelligently. So that is what we are learning right now. So I have as you might have seen in the last few videos, I wasn't able to write that good. In fact, like normally my handwriting is very bad. That too, when I have to write with the mouse, my handwriting was worse. But I from now on I have this tab with which you can hopefully understand my handwriting. So first, today I'm just going to yeah. So today we are going to look at like for in the last video we have looked at evaluation of object detection. That's how good was an object detection model. Like we have looked at how to evaluate this object detection model for a single image, right? So we are going to get this IOU, intersection over union, for each image. So we are going to have uh, calculate the loss function for each image. And now in this video we are going to look at how can we validate this object detection model for some collection of images. Let's say we have some images, and how can we actually validate uh, how good the model is. So first, before getting into this topic, I just want to share some important things that you have to learn in order for you to start. These are some things that you have to learn. So I'll just first I want to write some topics. So I just want to write something, uh, some topics that you are that are very common in machine learning, but we are going to look at them in the terms of object detection, of course. So and I'll just have we'll have this values. I'm just going to say. So the first thing you have to learn about, like I'll just write a map. Two negatives. So these are in the case of binary classification, these topics will occur. True negatives. I'll just improve my handwriting. So I'll just have we have two negatives, true positives. Let's say we have false negatives. And then we have false positives. So these are some things that are common in like machine learning. So hope my handwriting, like this is my real life handwriting. So we are going to have this different terminologies. So these are some terminologies, right? So these are some terminologies in the field of binary classification. So what is meant by true negatives is equal to. So what is true negatives means? You know, the actual value, y, the output of the actual target value of like in the test set maybe is negative, that is 0, and then true negative means our model also predicted 0. So in the terms of object detection, that means like in fact there is no bounding box in a certain area. So let's say uh, like just look at my video. So let's say this is the part where there is no human or there is no object. So this is the part there is no object. So if our model predicts no human here or no object here, then that is true. Like if you look at human object detection, detecting humans, like location of humans. So in this box that I'm drawing in my computer webcam, as you can see there is no human. So therefore like in real life there are no humans, and our model, and if our model predicted that there are no humans, then that is called true negative. So this, like, we don't have to learn more about true negatives in this context of this video. So like that's that. And then we have true positives. So, as you can understand by the name, uh, positives means there is a human face. So this object, so this location has a human face, and if our model predicts that in this location there is a human face, that means the prediction is a true positive. And then what is false negative? Understand, right? So there is no like false means the model predicted wrong. So let's say this is again, this is the area where there is no human, right? And then false negative means the model predicted that there is a human here. So if the model predicts there is a human or an object, in actuality there is no object there, that is called false negative. And what is false positive? Again, there is human here, human face here in actuality, but our model predicted that there is no human face here, then that is false positive. So that is the some of the important terminologies. I should have shared them in the case of binary classification. These are just names. Just try to remember these names, hopefully. And then now let's get to some more important, like these are also binary classification like functionalities. So these are some functions that can determine how good a classifier is. So these are two different two I think two completely different approaches in the case of calculating how good a model is. Of course, the first one you can see here, we can calculate the precision. So precision is a metric, to calculate how good a model is. So we have this formula, this little formula, which is equal to true positive. True positive I shared, I have in the context of object detection. Of course, true positive is there is a required object, there is the target object there, and our model predicts at the same location there is a target object. So I'm just going to make another statement just so you can understand. I have also faced the same issue when I was learning object detection. Right? So how are we going to predict? Like, let's say in object detection, right, there is not going to be one answer. Right? So if you have watched the last video, you might have understand that closer closer boxes will get like equal prediction. So let's say there are one box here, the actual target box, and then let's say the predicted box is approximately here, then we can consider that as the correct answer. Right? So that is what I shared you in the last video. If you have not watched the intersection over own union video, then make sure to watch that video. It will help you to get through this video. So first, yeah, I'm just going to share that true positive means we are not going to say that the prediction should be exactly intersecting or exactly the target box, but what we are going to say is it is going to be closer, right? So let's say we'll have a threshold how the IOU should be, and then based on that we'll detect if that is the correct answer or not. Hope you understand what is going on. And then yeah, so we are going to have this true positive divided by the true positive plus false positive. False positive again, like there is an object but the model is not able to predict the object. So this is a metric precision. So you can understand what is essentially happening here. Out of all the boxes in the target, how many are we going to, how many is the model able to predict, how many is object model able to locate, to be precise. And then we have this decall, right? So we are going to have true positive divided by, I'm going to say true positive divided by true positive plus false negative. So this is the recall formula. So again, what we are going to do is we are going to see here the meaning of the formula is out of all the what is false negative, there is no object, but the model predicted that there is an object. So out of all the predictions, how many of the predictions are right? And then you might observe that we have not used true negative anywhere because that doesn't make any sense in the case of object detection. There is an object and the model predicted nothing. Well, I don't think that is a very important metric, so therefore that it is not included in the formulas, in this precision and recall formulas. So now let's get to the main topic of this video, which is what is the topic of this video, which is mean average, precision. I'm just going to go. I don't think I'll share an example here. I'll just go through fastly. I'll go through it fastly. I'll try to show you what it is. So first, okay. So how are you going to calculate it? So first, so let's say in our test set, right? So we will use this mean average space precision in a set of tests, right? So like if you have watched the machine learning videos, you will know that in order to train a machine learning model, you'll have a training set and a test set. So you'll train the model on the training set, training data set, and then you can test the model, how good the model is performing on new images by using this new set called test set. So let's say we have the test set. So let's say for simplicity cases, let's say we have three images. Sorry, I'm sorry for that. Let's say we have three images. Image number one. So this is, let's say this is one image, and let's say, like, yeah, like this is one image. This is another image, and let's say this is the final image. So what are we going to do is, let's say there is one cat and one dog, one cat, one dog, one cat, one dog. So whatever that is, let's say we have some predictions. So what we are going to do is, as I have told you in the last video, each prediction box, each bounding box prediction will have its probability, right? So for each prediction bounding box, predicted bounding box, we are going to have its own probability, right? So what we are going to do is, based on the probability or confidence of the model, probability is also known as confidence. So based on the confidence of the bounding box written by the model, we are going to write it in the ascended form. So we are going to have each prediction, right? And then based on that, we'll have this row of, so for each prediction we are going to have the confidence, and based on that we're going to ascend this list, or descend this list, and then we are also going to have the precision and recall. So how are we going to calculate the precision and recall is, from the first we are going to calculate the precision recall. So we are going to go through like a for loop, and then we are going to update this precision and recall for each values. Hope you understand what's going on here. So that is like very simple, right? Like this topic is not related to neural networks. So this is just a evaluation metric to evaluate how good our machine learning or object detection model is. So we are going to have this number of patient values, right? So we are going to have this precision and recall values, and after we have this precision recall values that are in the descending order list by this conference matrix. So what are we going to do is, so we are going to draw a graph. I'm just going to, yeah. So yeah, we are going to draw a graph, right? So based on that, what we are going to do is, this will be the recall and this will be the precision. So we are going to draw the graph of precision recall, and then we'll have some values over time. So let's say that is the value. So we are going to get this graph, some type of graphs, and based on a function. So based on a function, we are going to calculate the area under this graph. So all the area under this graph, sorry. So we are going to calculate the area under this graph. So make sure. So before I'll tell you that, I'll just remind you that, like, we can calculate precision. We will calculate precision for only one class. So let's say we have two classes, dog and cat. So if we are going to calculate this table, so we are going to have this table for each class separately. So let's say this is the class for dogs. So this table is for dogs, and then we are going to do the same process for cats also. And then what we are going to do is, so let's say for dog, we will get a value. For dog we'll get a value. So let's say it is, I'm not going to say the value. So let's say it is 53%, anything like that. And then we are going to do the same thing for cats. So we are going to calculate the same prediction recall, and then for every prediction we are going to do this graph, and then we'll calculate the area, and then we are going to have this value. And then what we are going to do is, finally we are going to get the mean of both of these values. So we are going to have, I'm just going to say, so let's say I is equal to 0 up to n. Let's say n is the number of classes, and then we are going to add the value. So let's say v of, so let's say the value v, right? So what we are going to do is, we are going to calculate the average. We say 1 by n. So what we are going to do is, for every class, we are going to first calculate this values, this value, the area under the graph of the partial recall graph, and then we are going to get the average of these values, and then it will be the uh, final metric by which we can specify or assess the performance of the model, how good the model is performing on test. So that is for, like, these are like, I think the last two videos I have focused on evaluation. So before teaching you the architectures of the model, I just want you to learn some evaluation metrics by which you can evaluate. I also shared a problem, non-max separation. So from both of these videos, I just want you to learn about IOU, right? So how, what is intersection over union, and also the problem that non-max separation is solving. And then these are the important, these are important topics, and this is also is a very important topic on how to assess the performance of the object detection model. So make sure, so remember that we will do this process only after we train an object detection model. First we have to build the architecture, train it on training set, and then we have to test it. So thank you for watching. In the next video, hopefully, I think we'll be building a RCNN, regional CNN, right? In the next video, we'll build a RCNN from scratch, and then after that, we'll do YOLO algorithm, YOLO V1, V3, and then I think we'll do V5 and V8. So recently, V8 model came, like V8 and YOLO NAS, YOLO NAS. So these are both some, like, these are some powerful models, some powerful architectures um, of YOLO. So we'll also be looking at that, how to build that. And then thank you for watching, and then see you in the next video.